and we'll progress through the rest of those things over the next week or so. Okay. Like I said, we'll talk about points, lines, planes, segments, and how they can be congruent, what congruence means, what you should be able to do by the time we're done with this. We'll learn how to name and sketch geometry figures. And then once we know about points, lines, planes, we'll use those to build and develop the rest of the course. And then we'll talk about some segment postulates. We'll do books later. But you'll definitely have some homework. And if you have time in class, that'd be great. But we'll see how that goes. Okay? All right. First things first. Points, lines, planes. So anytime you're developing anything, right? We found this need for something called geometry, and we wanted to develop this. Anytime you discover something new, it almost always is built on some ideas or some concepts that you know exist, but you have a really hard time defining them, right? And so geometry is no different. We start with some undefined terms, what we call undefined terms, okay? And there are three. Those three undefined terms are points, lines, and planes, okay? We know they exist. We know that certain objects can be represented by points, lines, and planes. And guys, that's kind of the deal with geometry is if we can develop the ability to use geometry to model a lot of sort of real-world situations, then it makes things a lot easier, right? It makes life a lot easier. A point, the basic unit of geometry, it has no size. We call it, we talk about it as having no dimension, right? No size. It's infinitely small. It has only location, okay? And the way we name it is with a capital letter, okay? It would look something like that, right? That's point A. Okay? If we want to name it, right? If we want to give it a name, right? There's a point. If we wanted to name it, then we always use capital letters. Okay? So point A. Okay? A line is a straight arrangement of points. So now we're going to stack points next to each other. We're going to line them up next to each other. Right? And we'll create a line. And so for that reason, there are obviously infinitely many points on a line. Because a point doesn't have any size, it doesn't really take up any space, then we can identify an infinite number of points on a line. Okay? A line has infinite length, but no thickness, and extends forever in two directions. Okay? Infinite length that never stops. When we draw a line on our paper, we have to stop at some point because we can't draw to forever. Right? And so obviously that would look something like this. And so we'll stick arrows on both ends to represent a line. Right? So there's a line. Okay. Now, if we're going to name a line, we pick any 2 points on that line and use those 2 points. 2 points make a line, right? So we use any of those 2 points on that line to name it. Okay. So this guy we would call line AB. Now the problem here is that we're going to have line segments and rays and a lot of other things that we're going to want to use 2 points to name. And so we can't leave it just like that. So we introduce some symbols that we'll use along the way for our names. And since we're naming a line, then we simply put a line symbol above it. Right? Again, a lot of this stuff may just be some refresher for you. Okay? We can do that Sometimes you'll see a line labeled with a lowercase cursive letter, and we can certainly use that. So something like, instead of having the A and the B there, maybe you have like a lowercase L or a lowercase cursive M or N or any letter really, and we can use that guy to name the line as well. Okay? So we can call that lowercase L, line L or line AB, either one is good. Okay? So a line extends in one direction, well, two directions, but it has an infinite length, but no thickness, so it exists in one dimension, right? Points, no dimension, lines in one dimension, and we keep progressing up into a plane which has two dimensions, right? A plane has length and width, but no thickness, right? It's like a sheet of paper, only no thickness at all. So it has a length and a width, but no thickness. Okay, it's, again, planes extend forever, even though when we try to identify planes in the world around us, they're sort of finite, flat surfaces. They do extend forever. When we draw them, we have to stop because we can't draw forever, but just to understand that they do extend forever. And a plane, again, we're going to name a plane with 3 points. Right? So something like that. When we draw a plane, we tend to sort of, it's like a slanted box. We tend to slant it a little bit, right? So that might be a plane. Okay. And then you got two choices, 3 points. Docere desktop trial needs to go away soon. But 3 points, or what can't see there is a capital script letter. Capital script letter. So maybe this might be called plane M. Okay, we could do that. Or if we had 3 points, say A, B, C, then we can also call this guy simply plane ABC. Okay? Plane ABC or plane M. Either one is fine. Okay? So I always like to stop here and talk a little bit about where you see these things around you, right? Again, the deal with geometry and any math is trying to get to the point where you can use this to model anything around you, right? So, for example, points. Where are points in the room? Where do you see points in the room? What can we use a point to represent? Take a look around. What you got, Gabe? What about the flag? The whole flag?
Yeah.
The whole flag's a point? Does it look like a point? Does it look like a point? Okay. That's what I mean, right? I'm trying to lead you to where I want you to go. That's what I mean. What in here would look like a point if you were to draw it on your paper?
From one wall to the other?
Would be 1 point, or think about how would you draw a point on your paper? What would it look like?
A piece of tape.
There we go. Now we're talking, right? This screw head here, that tape, piece of tape, okay? Could be. You see what I'm getting at now? What else? See anything else?
Could it be used on like the corners? It's like something like, well, I was trying to say that with the flag.
Oh, okay, okay. But yeah, sure, right? Anywhere where two border lines meet, right? Could be a point, or in the very corner of the walls where the ceiling and the two walls meet, that kind of thing. Yeah, that's good. Good. What about lines? Where do you see lines? Where do you see lines? Zen, where do you see a line?
I see a line on the frame thing over there.
This guy?
Yeah.
Yeah, sure. That could be a line, right? What else?
Top of the board.
Sure. Top of the whiteboard there. That could be a line, right? So on and so forth. What about planes? Where do you see planes?
Ceiling tiles?
Sure. Tiles themselves, sure. Where else? Shelby, where else do you see a plane? What else could be a plane?
Door.
The door, sure. Right? Desktop, that kind of thing. Okay? So anytime we can find a way to let these theoretical objects represent some real world type stuff, then I think we're in pretty good shape. Okay? Good. More definitions for you. Collinear. What does it mean to be collinear? Right? What does co mean? Share. Share. That's pretty good. Co-captains, co-presidents. What were you saying, Gabe? Cooperative. Yeah. Find the word. You find co in there, right? Share. What word is in linear? So if you're collinear, yeah. Share a line, or in other words, you're on the same line. Okay? Collinear. How many points determine a line? 2, right? Algebra 1 class, you start graphing lines. I don't know how the teachers here like to do it, right? But the very minimum number of points you need to graph a line is 2, right? So with that in mind, can 2 points ever not be on the same line? No, they're always going to be on the same line, right? So when you talk about collinear, and then obviously non-collinear would be...
Teachers and students, at this time, we are having the state-mandated hearing screening testing. Please send all sophomores whose last name begins with A or B to the library conference room at this time. Thank you.
So then what we need is a third point to talk about collinear or non-collinear. Obviously would be not on the same line, right? So when we talk about collinear or non-collinear, you have to have a third point because any 2 points will always be on the same line. Just depends on which direction you draw. Okay? So collinear, non-collinear, the third point's got to float off of that line. I mean, you can certainly draw a line through these 2 points or these 2 points. You just can't draw one to capture all 3. That being said, coplanar. What's coplanar mean? Yeah, exactly. On or in the same plane. So how many points make a line? 2. Right? How many points do we need to determine a plane? Okay, remember lines, 1 dimension. They have an infinite length but no width. You're going to have a third one. Right? You're going to have a third one. Because it takes this third one to tell you which direction the width occurs. Right? Does that make sense? So we're going to have a third point to make a plane, which means can 3 points ever be non-coplanar? No. You can always draw a plane using 3 points or find a plane where they capture 3 points. And so it does require a fourth point to talk about coplanar or non-coplanar. Okay? So there's coplanar. You can imagine 4 marbles sitting on top of a table. So then in order for points to be non-coplanar, one of those marbles have to fall off. Right? So there's an example of non-coplanar. Okay. All right. Stop for a second and use what we just talked about. Okay. You have two other names for line PQ. Two other names for line PQ. And feel free to flip back and forth in your notes. I'll let you think about it for a second. Give me one other name for line PQ. Lizzie, what do you think?
ST.
Okay, and we're using this picture down here, right? So we don't want to change lines. We just want to find another name for it, right? So line PQ is this guy going through the plane. How else could we name that guy? Yeah, it can be that easy, right? Just make sure you put your arrows above it. That's pretty terrible, but still getting used to this thing. Right? Another name. How else could you name that line? Zen?
N.
Yeah. Just call it line N. Okay, that works. Need another name for plane R. Another name for plane R. Amanda, what do you think? I'm sorry? Okay. Flip back to your notes. How do we name planes? Flip back to your notes. How do we name planes? Okay. And then Nick, help her out. How else can we name plane R? You got it?
What did you use?
Say VP. Okay, I like VP. R is not a point, though. It's just that uppercase script letter. So VP S would work. Okay. Plain VPS would work. How about a second way? Said give two other names. How else could you name this guy? Nick, how about you now? You have another name? No? Don't think about it too hard. It's really easier than it looks. Yeah, go ahead. Sorry. PQV. Okay, now careful. Plane R is this guy right here, right? This little flat tabletop down here. Is point Q in that? No.
What about VPT?
VPT works. Okay. Quick word of caution. You don't want to use SPT. You don't want to use collinear points to try to name a plane, right? We talked about we do need 3 points, but we need one of those points to be non-collinear so we know where the width comes into play. Okay? So just be a little careful about that. You don't want to use that. Okay? Good. Oh, good. Pardon me, I go through puberty at 39 years old. All right. Name 3 points that are collinear. Go.
SPT.
SPT. Good. How about 4 that are coplanar? How about 4 that are coplanar? Yes, please. Tova?
SPTV.
SPTV works. Okay, SPTV works. Good. Any issues, questions there? Awesome. Okay? Now that we have these undefined terms, now we know that points, lines, planes exist, right? We can use those to develop the rest of our language for geometry, and we can start to actually have definitions for some stuff, right? And so the first we come across is a line segment, right? So lines extend forever. They have an infinite length, okay? Well, sometimes we want to represent things that have a length, a distance or whatever. And so we want to cut that line down so that we can possibly measure it. And so a line segment or a segment is what we do there. It consists of 2 points called the end points of the segment, and all the points between them that are collinear with the 2 points. So it's got to be all have to be on the same line. But a line segment has end points and all the points that are in between those end points on that line. Okay. Array. Array consists of the end point of an end point and all the points that lie on the same side of a second point. And I'll show you what I mean. Okay. Difference between a line segment and array. A line segment will cut both ends off of a line so that we can have an actual length to measure. Array will just cut off one side of a line. So array will still extend in one direction forever, and so making it very difficult to measure. Okay? So some quick examples here. This guy right here would be a segment. Okay? And then again, we want to differentiate between this segment and any other segment, right? And so we want to name this guy. When we name this guy, we don't want to say segment. Okay, that's not how we name stuff, right? We don't walk around calling you guys human. Hey, human, come here.
Okay.
Right? Right? When we talk about naming, and I say that and I try to make a joke about it because in my experience that pops up sometimes. Find 2 ways to name this segment. Segment and line segment. Thanks. Okay, that's not how that works. We want to be able to identify that particular segment. So, again, it's kind of like a line. We'll use the 2 endpoints, but we can't stop there because that could mean a line if we're not careful. And so we just use the segment symbol, which is just a little guy that was like a segment. Okay? But you got to use the endpoints to name a segment. You got to use the endpoints, right? If I can always identify as many points in here as I want, and that's on the line segment. But obviously, segment CB is not the same as segment AB. It's shorter, right? So make sure you're using endpoints to name them. Okay. Nothing wrong with flipping that around and calling that segment BA, but just use the endpoints. Okay. Array is similar in that it has an end point. Okay? But is different because it extends in one direction forever. Okay? It also has an infinite length like a line does. Okay? So all we need here is we have to identify the endpoint, and then we need a point that gives us the direction of the ray, right? Which way does it extend forever? And those are the 2 points we'll use to name the ray. Okay? So we call this guy ray AB, but again we have to have a symbol because we've got two letters to name other stuff. And so it it has to be this way. I mean, your symbol is going to look like a ray, or it should. Okay? But you got to make sure that your arrow side is above the directional point, not above the end point. Does that make sense? So since A is your end point, you don't want to put an arrow above the A. Okay? If we add a third point in here like this, be okay to name that ray AC? Would the name still tell you where it starts and still tell you what direction it goes? Okay. So that would be fine, right? Could you call that ray CB? No. It doesn't tell you where it starts, right? So be a little bit careful in how you name. All right? All right. Opposite rays. Opposite rays. They share the same endpoint and go in opposite directions. Shocker. Okay? Opposite rays. They share the same endpoint and go in opposite directions along the same line. So basically, opposite rays are going to look like a line. Okay? Okay? They're going to look like a line. Okay? And here's what they might look like. Okay? There's a line, right? Now all we need oh, can't see that very well, can you? That's a little better. Okay? So that's line AC, but you also find two opposite rays. So the two opposite rays are going to share an endpoint and then go off in opposite directions so that they are on the same line. Okay? And so if you want to talk about opposite rays, right? So then ray BA and ray BC would be opposite rays. Okay? But again, remember that your name of your ray has to start with the endpoint and then tell you the directional point. I don't care which way the ray goes. You always start with the endpoint and then name the directional point. Okay? So that would be your name down here. You just wouldn't be able to see it if I wrote it there. Okay? Good? Any issues, questions, anything there? Okay, good. Quick check. Give another name for segment GH. Anybody? Quick, go.
GJ.
Is GH and GJ the same segment? One shorter than the other one, right? I know where you're going with that. Go ahead.
HG.
Tell me your name.
Clinic.
HG. Would work. Just flip it around. It's really about the only other way you can name a segment, really, is to flip it around, because you have to use the endpoint. Okay? Good. Name all rays with endpoint J. Okay? Can you find them? Can you name them? I'll give you about 6 seconds to write them down. Got them? Give me one ray, Amanda. JG, as long as you write it like this. How about another one, Tova? Say it again. JH. As long as you write it like this. Another one, Gabe.
JF.
Sure. And how about the last one, Janie? JE works. Now, which of those are opposite rays? Yeah. Zach? Okay. HG. Is HG a ray? Opposite rays. You're naming. I think you're naming the lines. So we're picking out the lines. But which ones are the opposite rays? Actually, we have all the 4 rays here, right? Which of those 4 rays are opposite rays? That's what I'm asking. What do you think? Can you pick out a pair now? Rylan, help him out. JE and JH? Do ray JE and ray JH form a line? So not JE and JH, but JE and J, right, F. Okay? Make sense? And we got another pair. Right? Sophia, what do you think?
JH and JE, or JG.
Right. Okay. Good. Everybody good there? Okay, good. All right. I said before, right? The idea here is to be able to model a lot of different situations, a lot of different figures in the world around you with these theoretical models. It would be helpful if we could sketch them, right? If we're going to do that. So just some things you want to keep in mind. We're trying to make sometimes a 3-dimensional model fit on a 2-dimensional piece of paper, right? So let's try some things here. To sketch a plane in a line that is in the plane, what might that look like? Can you see it? Right? So we just need a slanted box, right? And then draw a line in that box. And that would be representative of that line being in the plane. Okay? It's kind of hard to see. It didn't specify the names of the plane or the line, so you can name them whatever. Here they're named plane M and line L, right? But just as long as your line is sitting in the plane, completely in the plane, then you're in good shape. Okay? Some of these can be kind of fun. Oh, already showed you, right? Sketch a plane in a line that does not intersect the plane. 2 things that do not intersect are called what? Yeah, parallel, right? So you just want to make your line and your plane look like they're parallel. And so kind of the opposite of up here, you'd want to sketch a little slanted box for your plane and then make sure that you draw a line that's not anywhere in the vicinity of the plane. And that would take care of that. Okay? Sketch a plane and a line that intersects the plane at a point. I'll give you a couple of seconds to try that one on your own. What would that look like?
D to the library conference room for hearing testing. Thank you.
Okay. Does that make sense? And so plane M, line L, just find a way to hide part of that line. Okay? Good. Sketch 2 planes that intersect in a line. Woo, this one's a toughie. Sketch 2 planes that intersect in a line. And so you'd want to show the 2 planes and you'd want to show the line. If you have any doubt as to whether 2 planes are going to intersect in a line or not, I mean, again, pick something around you, right? These 2 walls could be planes, and when they intersect, they intersect in that entire corner, and that entire corner could be a line, right? Two planes will always intersect in a line. So how would you go about doing that? This one's tough. This one's tough to draw, right? But the first thing you need is to draw a vertical plane. Doesn't have to be, but the easiest way to do this is to draw yourself a vertical plane. So from left to right, for those of you that don't know what vertical means. Okay, and then draw a second plane that's horizontal. And you would shade this plane a different color if you had different colors. Okay? But again, you want to use those dashed lines to show anywhere that a plane would be hidden. And I'll show you what that looks like. And then you want to actually draw in the line of intersection. So, where'd it go? There it is. Okay? So, dashed lines. At some point, these planes are going to be, parts of these planes are going to be hidden. So, however you drew yours, figure out which part of those planes would be hidden. And I don't know if you can see, you can't see this real well, but so here's your vertical and your horizontal planes. And if you can imagine, you wouldn't be able to see this back part of the horizontal plane, so you'd want to dash that in, right? I mean, it doesn't have to look like this, but this is probably the easiest way to draw it. And then you definitely would want to include the line where they intersect, right? And draw that line. Okay? It's a tough one. That's a tough one to draw. Okay? All right, so just trying to get to the point where we can use these figures to model some stuff around you. Okay? All right. So we know what a segment is, a line segment, right? How do we name the line segment? We talked about that already, right? We're going to use the two endpoints and then the segment symbol above it. Okay? But as I mentioned before, the reason why we talk about and we have line segments is so that we can create something that we can measure, and we can represent a length with or a distance with, right? And so if we want to talk about the measure of segment AB, we put a little m in front to represent the measure of segment AB. And obviously that's going to be a number. It's going to be a numerical value, right? Okay, another way we can talk about the length, or we can write down the length of a segment or the distance from the two endpoints is we just drop all symbols altogether and just write AB. So you ever see that? That means we're talking about the length of segment AB or the distance from point A to point B. And again, it's going to be a numerical value. Okay? And another vocab word for you here. So we've got new vocabulary, new words we have to understand the definitions of, the meanings of, and then we're also going to develop a new sort of set of rules that we need to follow, or not follow, but that we know are true because we've proven them, or not. Sometimes we have rules that we don't need to prove because they just are the way they are, right? And so rules in geometry that are accepted without proving it because it just makes a ton of sense are called postulates. And very often when we introduce a postulate, that's going to be something that you're going to say, why are we even talking about this? Because that makes just too much sense. And that's sort of the point, right? We accept them as being true without a proof. And that's why. They're called postulates. Okay? And the first one is called the segment addition postulate. And as the name indicates, It's what allows us to add segments together. And so what the segment addition postulate says is that if B is between AC, just between. In geometry, in order to be between, you have to be collinear. Okay? But if B is between A and C, then what we find is that if you take this segment AB and add it to that segment BC, then it would be the same as AC, right? I mean, that's kind of what we're talking about here. Okay, and that's what we get. Write this down too. And I'll redraw that. Okay? So if we add the length of AB to the length of BC, then it should equal the length of AC. And again, like I said, these postulates sometimes are going to be, yeah, okay. Okay? We just need to acknowledge them so that we know we can use that idea. Okay? And very often postulates we can sort of flip-flop back and forth. If we know that the length of AB plus the length of BC is equal to the length of AC, then that tells us automatically that B is between A and C. Okay, it has to be. Okay? There's another postulate called the ruler postulate. Okay? And the ruler postulate pretty much just says that every point has a one-to-one correspondence with the coordinate. And basically that just means that we can take a ruler and measure a segment. Okay? So if we want to measure the length of ST to the nearest tenth of a centimeter, right? All pretty easy. Take a ruler with some centimeters on it. And I don't know how much I want to tell you how to use a ruler. I think you probably know, right? But anyway, you use a ruler. So here we line up. The interesting thing that it took me a little while to figure out myself, and I don't know about you guys, but you know you don't have to start your ruler at 0, right? I don't know, I was like 27 before I figured that out. Right? You don't have to. But anyway, if you want to find the length of ST, just stick one endpoint on any of the nice, pretty marks on the ruler and then just measure it out. And this guy here. So your coordinate for S would be 2, and the coordinate for T would be about 5.4. And so in order to use what is technically the ruler postulate, you're just going to take the absolute value of that difference, which again, I think you guys seem like pretty smart people. You could probably figure that out. Okay, so the length of ST is 3.4. Okay? A lot of different ways we can write that, but there's one. The length of ST is about 3.4 centimeters. Okay? All right, another example here. The cities shown on the map lie approximately in a straight line. So we've got Lubbock, Texas, Tulsa, Oklahoma, and St. Louis, Missouri.
If you have any sophomores who...
How would you find the distance from Lubbock, Texas to St. Louis, Missouri? You might be able to see it better on your paper than up here. But from Lubbock to Tulsa is 380 miles. From Tulsa to St. Louis is 360 miles, right? So how would you find the distance from Lubbock to St. Louis? Anybody? Just add them up, right? But what I will tell you is it would be good if you get in the habit of writing out the segment addition postulate every time, and I'm going to show you why in a second. Obviously, this is pretty easy just to figure out. But if you get in the habit of writing out the segment addition postulate every time, then it'll help set up equations that we're going to solve later. Okay? But obviously, it's pretty easy, right? So since Tulsa is between Lubbock and St. Louis, then we're just going to add those together. So the distance from Lubbock to St. Louis is going to be equal to Lubbock to Texas plus Texas to St. Louis. And so it's an application of the segment addition postulate. And it'll get a little bit more complicated. But again, the point here is what I would do every time is when you have a point between two others is to write that thing out every time. Write out your segment addition postulate every time. And then plug in what you know and work from there. Okay, not so much in this guy do you need to do that. Okay. So the distance from Lubbock to St. Louis is about 740 miles. Okay. But sometimes that helps, especially when you're not directly using the segment addition postulate. And here's what I mean, right? So in this diagram, we want to find the length of GH. A tick more complicated than the last example, but not a lot. But again, here's where, if I were you, I would start off every one of these until you get really good with the segment addition postulate. Just write it out, right? So G is between F and H. And so what the segment addition postulate tells us is that FG plus GH has to equal FH. And then plug in what you know, right? Do you know the length of FG? Yeah, 21. Do we know GH? No, so just leave it GH, right? And then do we know the length of FH? Yeah. And then because we all got through Algebra 1 class, we know what to do here, right? Okay? And so GH is going to be 15. Right? So we'll get through this. Okay? Yes, question?
Couldn't you easily just take 36 times 21 and put the
Absolutely. Yeah, and that's what I mean. The map example on that one are pretty easy to sort of figure out, right? It's just there are going to be times where starting with the segment addition postulate with just the letters, right, is going to be helpful. So I'll keep taking the long way for a little bit, but if you can get there faster, absolutely. Okay? All right, so segments can be, since segments have lengths, you can have two segments that have the same length. And in geometry, that's called congruent, right? Two segments are congruent segments if they have the same length. Two segments are congruent segments if they have the same length. And check out that symbol. Okay? It's an equal sign with a little squiggly above it. That means congruent. Okay? We know what equal signs are. I mean, we've used those all the time. If you want to talk about the actual numerical lengths of two segments, then we talk about them being equal. Numbers can be equal. Okay? But if we're talking about geometric figures being the same, then we flip over and talk about them being congruent. And so you got to be careful about your symbols. Again, I told you it sounds very specific or too specific. But again, we're developing a new language, a new way of talking about things and writing about things. Okay. All right, so congruent segments. Compare segments for congruence in your next example. We've got some points that we're going to put in the coordinate plane. The coordinate plane is another fantastic way to model anything that you want to. Maps, as a matter of fact, I don't know, last time you guys actually held a paper map. Okay? But it's just one big coordinate plane, if you ever look. Okay? It's a great way to model something where you need a point of reference. Okay? But if we take these 4 points and put them in the coordinate plane, then we want to try to figure out if segment JK and segment LM are congruent. Okay? So the first thing we want to do is plot these points out. Right? And then we've got our segments, right? So now you see segment JK and you see segment LM. We could certainly create other segments in here if we really wanted to. I mean, there's absolutely nothing wrong with creating segment JM and segment KL or any other combination that you want. Again, any 2 points determine a line, and from a line we can create a line segment. But these are the two that we want to take a look at. And so now all we got to do is determine the length of those two segments. Right? And so we'll find the length of the horizontal segment using the x coordinates, right? This hopefully rings a little bit of a bell to you from Algebra 1. But if they're vertical and horizontal segments, then you can just use the x coordinates and the y coordinates. Okay? So we use the ruler postulate. So to find the length of JK, the y coordinates are the same. So we just use the x coordinates. Right? So 2 minus a negative 3. 2 plus 3 is 5. Always absolute value. That's what those bars, right? I didn't talk about this, but these guys are absolute value bars. Why are we talking about absolute value? Why are we using absolute value in the ruler postulate? Absolute value is always what? Always positive. Right? How many of you guys, your pencils are negative 3 inches long? We don't do it, right? So length is always positive, so we always want to make sure that we're taking the absolute value. Because the difference in your two coordinates might be negative, and we don't want to try to report a negative length. That doesn't make any sense, right? And then, so for your vertical segment, your y coordinates are the only ones that change, and so we'll just use those to find the length, right? And so again, using the ruler postulate, your two y coordinates for L is 3 and for M is negative 2. So we, again, the order doesn't really matter. We go negative 2 minus 3 is negative 5. Absolute value is 5. Therefore, JK is 5, LM is 5. Are those two segments congruent? Yeah. Okay, so JK and LM have the same length. So JK and LM are congruent. And that's how we're going to write it. Segment JK is congruent to segment LM.
Moors whose last name begin with H through K, please come to the library.
Okay? And that ends for us. Huh?
Is